Welcome. I'm Dr. Larry Sterna. In this video, we're going to begin the discussion of magnetism. Magnetism is a fascinating subject. You'll have to learn how to draw arrows in 3 dimensions and work with the right-hand rule. I hope you enjoyed this topic. Let's begin. The discovery of magnetism is attributed to the ancient Greeks, who found that a particular iron ore called magnetite, an oxide of iron, had the property that it could attract other pieces of iron to itself. Very peculiar. Then they discovered that a piece of iron that did not have this property could be magnetized by stroking it with a piece of magnetite. So that this new piece of iron now had the property of being magnetic, and it could attract other pieces of iron to itself. Although this was a fascinating discovery, it did not have large significance until around 11 to 1200. It was discovered that if you suspended a magnet from a string, it would align in a north-south direction. The discovery of the compass was a tremendous benefit to navigation, the ability to sail the seas. This was truly a discovery of enormous significance. Let's look at the relationship between a bar magnet and the compass. If you hang a bar magnet from a string, one end of the magnet always points to the north, one end of it points to the south. The end that points north is defined as the north end of the magnet. The end that points south is defined as the south end. If you label the north and south ends of the magnet, it's very convenient. You hang it from a string, you know which way is north, you know which way is south. So the north end of the magnet points to the northern direction on the Earth. If we draw an arrow pointing north, we also use that arrow to define the direction of the magnetic field. We say the magnetic field points in that direction from the north end of the magnet. It was also discovered if you have 2 bar magnets that the north end of one magnet will be attracted to the south end of the other magnet. Very interesting, because it was Gilbert who understood that the Earth is a giant magnet with its own magnetic field. Therefore, if the north end of a magnet is pointing to the north end of the Earth, and if the north end of a magnet is attracted to the south end of another magnet, it means that the north of the Earth is a magnetic south pole. There's a geographic north pole we call the Arctic, happens to be the magnetic south pole of the Earth. Likewise, since the south end of the magnet points to the south, the geographic south pole of the Earth, what we call Antarctica, is a magnetic north pole. This is not related to some kind of magnetic reversal of the Earth. These are definitions based on how the compass was defined. I said that a magnet has a north pole and a south pole. If we break that magnet in half, could we obtain a pure north pole and a pure south pole? No. If we break it in half, the 2 halves will both have a north and a south pole. Magnets always and only occur as dipoles with a north and a south. Not only do they have a north and a south, but they have equal amounts, north and south. You can have an excess of north, you cannot have an excess of south. You only have equal amounts of north and south pole. In other words, magnetic monopoles, a pure north or a pure south, do not exist. Now, if we look at this picture, the green arrows represent the magnetic field direction, or we could say the magnetic field lines. The field lines proceed out from the north end of the magnet. They wrap around, they enter the south end of the magnet. Looking at that, we might think of positive and negative charge. Positive charge is a source of electric field. Negative charge, we say, is a sink for electric field. Can we view the north and south magnetic poles in the same way we view charge? The answer is no. The north end of a magnet is not a source of magnetic field. The south end of a magnet is not a sink of magnetic field. Only on the outside of the magnet do the field lines proceed from the north and enter the south. If we could look inside the magnet, we would find that the field lines go from the south to the north. The magnetic field lines do not have a starting point or a stopping point. No beginning, no end. They're all continuous. They loop around. They may come out of the north into the south, but inside the magnet, they go from south back to north. B field lines are continuous loops. Look at that term, B field. The electric field, we use the capital E to represent the electric field. Magnetic field is represented with the capital B. Whenever I say B field, I mean magnetic field. I want to introduce a new term called the magnetic moment. For this quantity, I use the Greek letter mu with an arrow on top to indicate that it is a vector. Let's start by considering some magnetic field B. Magnetic field is also a vector, so I use capital B with an arrow on top. The green arrows, all pointing up, represent the magnetic field lines in some region of space. Magnetic field is something that exists in a region of space. What's the source of this field? Well, there can be many things that produce a magnetic field. We could even assume this is the magnetic field of the Earth, and all the arrows are pointing north. Now we place a bar magnet in the magnetic field. What's going to happen? Well, if the magnet is free to turn, free to rotate, the B field will exert a torque to align the magnet. This is just like the compass. If you hang a magnet from a string, it's going to align in a north-south direction like that. This torque is going to be proportional to the strength of the field, the strength of the dipole, and it's related to the angle between the two. If you know the strength of the field B, you measure the torque, you can calculate how great is the magnetic moment mu. The larger the magnetic moment, the larger the torque. Or alternatively, if you know the magnetic moment mu, you measure the torque, you can determine how large is the magnetic field. I said it's a magnetic moment's a vector. It represents the strength of this magnetic dipole, and it indicates the direction of the magnetic dipole. I started this video talking about iron magnets. What is special about iron that allows it to become a magnet? Well, iron has two special properties. The first property is that iron has unpaired electrons in d orbitals. Each unpaired electron has an electron spin, and in the d orbital has an orbital angular momentum. The combination of the electron spin and the orbital motion produce a small magnetic dipole moment. Each unpaired electron is a small magnetic dipole. That's the first special property. The second special property of iron is that in a piece of iron, the atoms that are adjacent to one another have unpaired electrons that will align in the same direction. Therefore, a group of nearby iron atoms will have their electrons aligned in the same direction and will produce a small magnetic moment, larger than an individual electron, but a small magnetic moment. These regions of electron magnetic moments that are aligned are called domains. In a piece of non-magnetized iron, there are many domains as illustrated in this picture. Actually, there are vastly more electrons, vastly more domains, but this is just an illustration. Each arrow represents a small magnetic moment from an electron. The little areas where magnetic moments are aligned in the same direction are called domains. But in a non-magnetized piece of iron, the domains are randomly oriented relative to one another. Although there is a small magnetic moment in each domain, the total magnetic moment is zero. However, if you slowly and repeatedly expose this piece of iron to another magnet, you can get all of those domains to line up with one another. When you have all the domains aligned in the same direction, you produce an overall magnetization, a piece of iron that is magnetized from end to end with all those electron magnetic moments pointing in the same direction. Now you have a bar magnet with a north pole and a south pole made up from all of those electron magnetic moments. This picture and this model explains two things. It explains the origin of the magnetization in a piece of iron. It also explains why, if you cut this thing in half or cut it into many pieces, you still have a north and a south pole. Because every piece is still made up of those electron magnetic moments that are oriented in the same direction. If you cut the piece smaller and smaller and smaller, eventually you get down to a single atom of iron or even a single electron. You'd still have a magnetic dipole moment, but you wouldn't be able to separate it any further. You couldn't slice an electron into two parts. In this introductory video on magnetism, I talked about the magnetic field and the magnetic dipole. These are the fundamental concepts in understanding magnetism. In the next video, talk about the magnetic force on a charge. See you there.